This video is entitled Sampling Distributions and the Central Limit Theorem.
Now the sampling distribution that we are primarily interested in is X bar. Basically we're going to be dealing with the normal distribution situation where X bar is our random variable instead of just X. Now the first important theorem that comes from this section is the central limit theorem. And it's very important and very useful in statistics. Now the central limit theorem is an important relationship based on the sample size of your data. And down here it tells you that if samples of size n, where n is greater than or equal to 30, are drawn from any population with a mean mu and standard deviation sigma, then the sampling distribution of sampling means approximates a normal distribution. The greater the sample size, the better the approximation. So what this essentially says is that let's suppose you had some distribution that was non-normal for random variable x, and then we took sample sizes of 30 or more and created a new random variable x bar, which the x bar would be the average of all the values. So what you would have is you would have a bunch of different variables that were averages of groups of 30 out of that population or more. And if you plotted those would approach a normal distribution. So that's where this theorem is really useful, how it kind of can convert any distribution to a normal distribution as long as you choose a large enough sample size. Now the second part of the central limit theorem says that if the population itself is already normally distributed, then the sampling distribution will be normally distributed. So it doesn't have any effect there. Now we are interested in X bar, basically, as our random variable and how this applies to the normal. And let's look at how we come up with our mean and standard deviation, which will be very critical when we are calculating our normal probabilities. Now the population mean of all those individual sample means that I was mentioning will just end up being equal to the equivalent of the population mean. So no big change there. So it's just the mean that they give you in the problem will be the mean that you use in your calculation. Now here's where it becomes interesting with the standard deviation. So the standard deviation for all of these X bars is not the same as the standard deviation of all of the individual values X. The standard deviation for the random variable X bar will be the standard deviation of the population divided by the square root of n. Now that's going to be very important that we remember to take our standard deviation and divide it by the square root of n. Now let me just show you a couple of graphs here, and let's take a look at what's going on here. This graph number 1 shows just some population distribution with just some sort of kind of mountain shape looking graph, certainly not normal. So there's no way that you could calculate a normal probability on random variable x. I mean, it would be an inaccurate result to say the least. But if you have, look how the distribution of the sampling means if n is greater than or equal to 30 and you were plotting them as X bar values, the averages of all those different 30 sample sizes out of the population, whatever size that may be. Notice that graph then becomes normal shape. So to me, that's the beauty of this theorem, is that you can use the normal distribution as long as you're willing to use random variable X bar with sizes of 30 or more sample size. Now the number 2 just shows if your original population is normally distributed, that the distribution of sample means X bar will be normally distributed for any size n. So if your original population is normally distributed, the n doesn't have to be more than 30. It can be anything. And the graph is a little bit narrower because when you take your standard deviation and divide by the square root of n, it gets smaller. And as we learned earlier on with the normal distribution, that if the smaller the standard deviation, the narrower the graph gets. All right, so let's see. Now, let's look at a problem involving the mean and standard deviation of x bar. This problem number 1 says the National Weather Service keeps records of snowfall in mountain ranges. In a certain range, the annual snowfall has a mean of 100 inches and a standard deviation of 14 inches. Suppose the snowfalls are sampled during randomly picked years. For samples of size 49, determine the mean and standard deviation of x bar. All right. Now, from backup board, let me write these down. That mu of x bar is just mu of the population. So that's just going to be 100. Now, here is where mistakes are likely to be made on the standard deviation. Many times students would look at the number 14 and their eyes would light up thinking, that's my standard deviation, 14. That's your standard deviation for x, but it's not your standard deviation for x bar. So for samples of size 49, my standard deviation for x bar will be the standard deviation 14 divided by the square root of the sample size 49. All right, this one I think I can do without a calculator. Square root of 49 is 7. 14 divided by 7 is 2. So therefore, that backs up the answer they have marked here. Answer A is correct. But you can see answer B would be real easy to fall into if you weren't paying attention. So let's get down here now and look how probability interacts with the central limit theorem, and mainly how to calculating normal probabilities. So the main difference between this and what we have already learned with the normal distribution, really and the only difference, is our standard deviation. Remember before, our z-score formula looked like this. X minus mu over sigma. But now, look at my denominator. It's sigma divided by the square root of n. So as long as we do that, and then of course the way we interpret the z-score, either using the calculator or using the chart, will be the same. So as long as we remember to do this, we will be in good shape. Now, oftentimes where students have trouble on this is how do we recognize when we're calculating a normal probability for x bar and not random variable x? Like, how do we distinguish the difference when we read a problem? Now, there are two key differences. First of all, the sample size will be greater than 1. For example, instead of choosing one house, we might choose 40 houses. Other problems I've done, choosing one SAT score, we'll choose a group of SAT scores. Or choosing a monthly electric bill, I believe I did an example on that. We would choose a group of monthly electric bills and calculate, and we won't calculate their average, but that's the probability we want to figure out, is based on the average of that sample size. Now, also, the question will sort of guide you there if you're paying attention. The instructions will tell us to find the probability that the mean is less than, greater than, or between two values. So it's going to tell you there's more than one value, and the question will be asking for the mean. It might say average, but many times it will say the mean is less than or greater than. That's how we would know that it's the sample mean, the x bar. All right, so let's look at some problems here, and these and I'll point out the key features as we do these. All right, let's see. A coffee machine dispenses normally distributed amounts of coffee with mean of 12 ounces and a standard deviation of 0.2. If a sample of 9 cups is selected, find the probability that the mean of the sample will be greater than 12.1 ounces. Now, you might notice here that when you look at the n, you might be thinking, based on what was said earlier in the notes in this section, don't we have to have 30 or more to apply this technique? Well, the central limits theorem says that only if your population is not normally distributed. Notice here that since our population is normally distributed, n can be any size. So that we're okay with that. If it didn't say normally distributed, the sample size would have to be more than 30 or more. So let's see what we have here. So we have a mean of 12. And a standard deviation of 0.2. However, once again, that standard deviation is for x. That is not our standard deviation that we need. Now, you can calculate the standard deviation that we need first, or we can just set it up in our z formula, which our z formula basically is going to look like this. Probability, well, first I'll put as x bar. X bar is greater than 12.1 ounces. So now we have to convert that to z using our new conversion for standard deviation. So let's do that. Z is greater than 12.1 minus the mean x bar, which the mean x bar is the same as mu is 12, divided by the standard deviation, but the standard deviation of x bar is the standard deviation of the population divided by the square root of n. So we need that z-score to two decimal places, whether using the chart or the calculator. So let's put the calculator up here and see what that z-score is. I'll do this all in one step, but I'll be careful how I use my parentheses. 12.1 minus 12 divided by, now I have to wrap parentheses around this also on the bottom. 2 divided by, I'm just going to put 3 because the square root of 9 is 3. Obviously, they won't always be perfect square roots like that, but I have to have that parentheses there. So let's see what this z-score gives me. 1.5. Okay. Now I'm going to do these using the normal calculator without, the TI calculator with the normal CDF function without going back to the chart. I'm going to assume that by now we know how to read the chart, but I do want to mention that, remember, for greater than, you have a couple ways. You can either do 1 minus this value, but in my class, most of the time you've seen me do this, where we flip it over and change the sign. Because remember, the chart is always based on less than, area to the left. So if you're using the chart, you would use negative 1.5. Now in the calculator, we don't have to flip it up so much. We can just kind of do this. We can go second, vars, normal CDF. I'll just go 1.5 comma 100 to represent infinity. Enter. 0668. So let's see if that looks like my answer. And yes, it does. 0668. Answer C. All right, let's try another one. So we're going to kind of cover, greater than's, less than, and between two numbers. The weights of fish in a certain lake are normally distributed with a mean of 11. That's just for x. Standard deviation for x, which is 6. If 4 fish are randomly selected, n equals 4, what is the probability that the mean weight will be between 8.6 and 14.6 pounds? So notice the key things here. We're selecting more than one item, and notice the question phrasing is, what is the probability that the mean weight? Right there. That tells me my random variable will be x bar. So let's write this. So we're going to have 8.6 on the low end. 14.6 on the high end. Now we need to convert both ends to z's. So let's do that then. That'll be the probability of 8.6 minus 11. Okay, once again, here comes the standard deviation part. 6 divided by the square root of n, 4. And now that changes this to z. And on the upper end, I'm going to have 14.6 minus 11 divided by 6 over the square root of 4. So let's go back to the calculator and see what these two values are going to be. Forget this, let's see. 8.6 minus 11 divided by 6 divided by 2, square root of 4. Enter. And then I'll put the same in there for 14.6. Second insert. 14.6. Here we go. 1.2. So my range of z values will be negative 0.8 to 1.2. Oh, made a mistake there. Yeah, negative 0.8 to 1.2, excuse me. So we can erase that 1 right there. I can leave it. I'll put the negative right here. Negative 0.8 to 1.2. So if you were using the chart, you know, it would be the table value at 1.2 minus the table value at negative 0.8. You'd look those up, subtract the 2. The answer has to be positive because it's a probability. It has to be between 0 and 1 also. But I'm going to use the normal CDF command here. Normal CDF, enter, negative 0.8, comma 1.2. Enter, looks like about 0.6731. Let's see how we did there. Okay, it's a little off, but that's all right. You won't have answer choices that close together on an exam, so I think that's not going to be an issue at all, so that's quite all right. So, all right, let's proceed with another problem here. Study of the amount of time it takes a mechanic to rebuild the transmission for a 92 Chevy Cavalier shows that the mean is 8.4 hours and the standard deviation is 1.8. All right, so mean is 8.4, mean of x, standard deviation of x is 1.8. If 40 mechanics are randomly selected, find the probability that their mean rebuild time exceeds 8.7 hours. Once again, the two key things, we're selecting 40 mechanics, not just one mechanic, and finding out what probability that their time is. It's an average of those 40 mechanics. And also, once again, the word mean appears. So that tells me again that's random variable x bar. Now notice there's something interesting in this problem. It's the first time this has happened yet. Is nowhere in this problem does it say anything about being normally distributed anywhere in there. All right, well this is where the central limit theorem takes effect. That's because our n is now greater than or equal to 30. In fact, it's 40. So since it's more than 30, the original population does not have to be normally distributed. The central limit theorem says x bar will be close enough to being normally distributed to where we can use the normal distribution. So that doesn't affect anything in our calculation, but I just wanted to mention that to you in case you thought there was missing information there. There is not. That's what the central limit theorem is all about, is that more than 30 issue. So we're good to go. We can set up our question here. probability of X bar greater than 8.4. Exceeds is the same as greater than 8.7, excuse me. Exceeds 8.7 hours. So once again, we convert this to Z. It's the probability that Z is greater than the X bar value, 8.4, minus the mu, 8.7 minus 8.4. Divided by the standard deviation, which is 1.8 divided by the square root of 40. You know, that mistake I just made for a second there in the numerator, I was just about to mention, ironically, is, you know, watch for the fact, I've seen, you know, students do this, get these numbers backwards. So you have to, you know, the X bar goes first and the mu goes second. I've seen that get reversed, which will, of course, affect your answer. So let's see what we got this time. We're going to say 8.7 minus 8.4 divided by, start parentheses, standard deviation is 1.8. Now I certainly will have to put the radical in there because the square root of 40 is not a nice integer number. So there we go. So we have the mean, subtracted the standard deviation, dividing by the square root of n. Very important. So it looks like about 1.05. So I'm going to use that as my Z. So now I'll come back over here. And we'll say that equals probability that Z is greater than 1.05. Once again, it's a greater than. You can flip it over and change the sign if you're using the charts. So you would look up negative 1.05 to get your answer. And you can certainly draw pictures of this if it helps you too. Like, for example, if I were to sketch a normal curve, even if I want to put it in terms of, well, actually I shouldn't put it in terms of X because X isn't normally distributed, so I better use the Z here. But remember on the standard normal distribution, Z is in the middle, 1.05. So you, just by looking at that picture, that tells you your answer's got to be less than 0.5 because it's less than half. That would help maybe eliminate some answers, but all these answers are less than 0.5. So that might help you if you accidentally looked up 1.05 and thought that was the answer, but that area is going to be bigger than 0.5, so that would tell you that it was wrong. So the picture is totally optional. So look up negative 1.05, or normal CDF would be second distribution, normal CDF, 1.05, comma 100 for positive infinity. So it looks like it's about 0.1469. And okay, looks like we've got that as an answer already, 1469. Very good. I believe I have two more examples here, and then I will be completed this section and leave up to you to practice this on your own. So let's see, the average number of pounds of red meat a person consumes in a year is 196 with a standard deviation of 22 pounds. If a sample of 50 individuals is randomly selected, find the probability that the mean of the sample will be less than 200 pounds. Just like the last problem, since our n is more than 30, it's 50 in this case, the central limit theorem applies. It does not have to tell us anything about the normal distribution in the problem, but we will be able to use the normal distribution. All right, so mu is 196. Standard deviation is 22. N is 50. And our question is, find the probability that X bar is less than 200. Because once again, there's the, the more than one sample, and there's the key word there, the mean. Find the probability that the mean of the sample, that's how we know it's X bar. with a little practice between working these, mixing them in with the other ones on my review, that should help you, make the distinction between the two. So let's convert this over to a z. So we'll take our x bar, which is 200, minus the mean of 196, the mu of x bar, which is the same as the mu, and move this down a little bit, divided by sigma over the square root of n, 22 divided by square root of 50. So let's convert this to a z-score. Clear that. We'll go 200 minus 196 divided by 22 divided by square root of 50. Close my parentheses. We're looking at a z-score of 1.29. So probability that z is less than positive 1.29. Okay, whenever you have less than, that's what your normal distribution chart is based on, is less than. So you don't have to manipulate the number. You just look it up as 1.29 using normal CDF. I'll go second. Now this, I have to start this off with negative 100, representing the idea of negative infinity, up to the value 1.29, like so. Enter. Looks like about 0.9015 would be my probability that X bar is less than 200. In other words, that the average of those 50 individuals would have consumed less than 200 pounds of meat. Let's see, what was it again? 9015. And there it is. Answer A. All right, one more problem for this section. Hopefully this has helped clarifying this for you. Hopefully it's making it clear. Assume that heights of women are normally distributed with a mean of 63.6 inches and a standard deviation of 2.5. If 75 women are randomly selected, find the probability that they have a mean height between 63 and 65 inches. So I haven't written this down before, but I'm going to go ahead and kind of write this here. It's kind of what I said for the last two problems. Just letting you know the central limit theorem applies. Same reasoning as the last two. So let's set up our, well, I'll write down the values again here. Let's see. The mu is 63.6. Standard deviation is 2.5. N is 75. Mean height between 63 and 65. So that puts X bar right between 63 and 65. So we convert these both to Z's. So it'll be 63 minus 63.6. And standard deviation divided by the square root of n. So it'll be 2.5 divided by the square root of 75. Oh, close that off too soon. Which is Z, which is 65 on the high end. .5 divided by square root of 75. So let's go to the calculator. 63 minus 63.6 divided by 2.5 over the square root of 75. Negative 2.08. Oh, that's the low end. Now I have to get the upper z value. So I'll go to the calculator and I'll do the nice little second enter function. Change 63 to 65. That's all I have to do. Enter 4.85. Now, this is mentioned in one of my sections on the normal distribution notes that if your value's off the chart, either high or low, it's not going to be real critical. Like you could use 0.9999. You could even use 1 for that 4.85 if you wanted to, or 9998. I think the chart has is the largest number. Yeah, you won't find 4.85 on the chart, but that's not going to be a problem. And same thing on the smaller end. You could actually use 0.00001 if it had been negative 4.85, or even 0 really wouldn't hurt to use. And because like I said, the answers are not going to be that close together. I'm not going to have answers that are like 1/10,000th apart from each other. So in other words, this is, I'll just kind of draw an arrow here. That's approximately 1 on the chart. Well, I'm going to do a normal CDF, though. Negative 2.08, comma, 4.85. I mean, I could probably put 100 there, and it won't matter for that. In fact, I'll do that just for fun here. 4.85 is pretty, it'll make some difference, the later decimal places, but 4.85 is pretty far out there on the standard normal distribution. Yeah, see, it didn't even change until the 6th decimal place. So, yeah, really didn't matter too much. So we'll go with 9812. Okay, just slightly off a little bit here. But like I said, that's not going to be a problem. Okay, well that concludes this lecture on the central limit theorem and finding probabilities for the random variable x bar. So I wish you the best of luck and keep practicing to enhance your skills.